ideas of modern science, offering us a window into the very building blocks of the universe. It fundamentally challenges our understanding of how the world works, and in many ways, it defies our intuition, especially if we're used to thinking in terms of classical physics. Today, I want to take you on a journey through the basics of quantum physics, touching on its key concepts, its strange behaviors, and how it reshapes our current view of reality. So let's start with the notion that everything in the universe, from the smallest particles to the largest stars, is governed by physical laws. For centuries, classical physics, grounded in the work of Isaac Newton, dominated our understanding of these laws. In the classical world, things behave in predictable ways. If you throw a ball, you can calculate its trajectory based on its speed, angle, and the forces acting on it. This deterministic worldview worked wonderfully for explaining the movement of planets, the flow of rivers, and even the mechanics of machines. But when scientists began to study matter at an extremely small scale, atoms and subatomic particles, they realized that the rules of classical physics didn't seem to apply anymore. This was the birth of quantum physics. Quantum physics is the branch of science that seeks to describe the behavior of matter and energy on the tiniest scales imaginable. The level of atoms, electrons, photons, and even smaller particles. What makes this field so interesting and so difficult to grasp at first is that on this scale, things don't behave in the same way that they do in our everyday world. One of the most fundamental concepts in quantum physics is the idea that particles, such as electrons, aren't just particles in the way we normally think of them. In fact, they can also behave like waves. This is known as wave-particle duality, and it's one of the key discoveries of quantum physics. In the early 20th century, physicists proposed that particles like electrons could exhibit wave-like behavior under certain circumstances. This was soon confirmed in experiments, most famously in what's called the double-slit experiment. In the double-slit experiment, the scientists shoot particles like electrons through two narrow slits onto a screen behind them. If you were shooting regular particles like tiny marbles, you would expect them to pass through one slit or the other, creating two bands of particles on the screen behind. But when this experiment is done with electrons, something astonishing happens. Instead of behaving like marbles, the electrons create an interference pattern, much like waves of water passing through two slits would. This suggests that electrons are not just particles, they also have wave-like properties. But it actually gets even stranger. If you try to observe which slit the electron goes through, whether it behaves like a particle or a wave, its behavior changes. If you measure which slit it passes through, it seems to act like a regular particle, creating two distinct bands. But when you don't observe it, it acts like a wave, creating the interference pattern. This is a fundamental aspect of quantum physics. The act of observing or measuring something on the quantum scale actually changes its behavior. This idea, known as the observer effect, is one of the most puzzling quantum system, such as an electron, can exist in multiple states at the same time until it's measured. To illustrate this, let's consider the famous thought experiment known as Schrodinger's cat. Imagine a cat in a sealed box with a device that can release poison based on the decay of a radioactive atom. According to quantum physics, the radioactive atom can be in a superposition of both decayed and not decayed states. Since the poison's release is tied to the atom's decay, the cat, too, must be in a superposition of being both alive and dead, at least until we open the box and observe it. This strange thought experiment demonstrates how quantum superposition challenges our everyday understanding of reality. The phenomenon of superposition is also closely related to the concept of quantum entanglement, which Albert Einstein famously referred to as spooky action at a distance. Quantum entanglement occurs when two or more particles become linked or entangled in such a way that the state of one particle is directly connected to the state of the other, no matter how far apart they are in space. This means that if you measure one particle, you instantly know the state of its entangled partner, even if it's on the other side of the universe. This instantaneous connection defies classical notions of space and time and has puzzled physicists for decades. But despite its weirdness, entanglement has been experimentally verified and even forms the basis for emerging technologies like quantum cryptography and quantum computing. Another key feature of quantum physics is the uncertainty principle, formulated by Heisenberg in the 1920s. The uncertainty principle states that there are certain pairs of physical properties, like position and momentum, that cannot both be known with absolute precision at the same time. The more precisely you know one, the less precisely you can know the other. For example, if you know exactly where a particle is, you cannot simultaneously know its exact speed, and vice versa. This uncertainty is not due to any flaw in our measuring instruments, but is an inherent feature of the quantum world. It reflects the probabilistic nature of quantum physics, where outcomes are not determined with certainty, but rather with probabilities. The probabilistic nature is perhaps one of the most difficult aspects of quantum physics to reconcile with our classical intuition. In classical physics, if you know enough about a system, you can predict its future with a degree of certainty. If you know all the forces that are acting on a ball, you can predict exactly where it'll go. But in quantum physics, even if you know everything about a quantum system, you can only predict the likelihood of different outcomes. For instance, you can't say with certainty where an electron will be, only that there's a certain probability of finding it in a particular place. This shift from certainty to probability marks a profound change in how we understand the universe at its most fundamental level. One of the most important mathematical tools in quantum physics is the wave function, a complex mathematical object that describes the probabilities of a quantum system's various possible states. The wave function gives us all the information we can know about a quantum system, but it doesn't tell us definitively what the system is doing at any given moment. Instead, it describes a range of possible outcomes, each with its own probability. physics also fundamentally challenges our understanding of energy. In classical physics, energy is often thought of as continuous. You can have any amount of energy in a system. But in quantum physics, energy comes in discrete packets, or quanta. This idea was first introduced by Max Planck in the early 1900s to explain the behavior of light. Planck proposed that light is not emitted continuously, as classical physics would suggest, but in discrete packets called photons. This marked the beginning of quantum theory. Now, later, Einstein used this idea to explain the photoelectric effect, showing that light behaves not only as a wave, but also as a stream of particles, or quanta of energy. The development of quantum theory in the early 20th century revolutionized our understanding of the universe, and many of its predictions have been confirmed through experiments. Quantum mechanics successfully explains a wide range of phenomena that classical physics cannot, from the behavior of electrons and atoms to the properties of semiconductors used in modern electronics. It's also the foundation for much of modern technology, including lasers, transistors, and MRI machines. Despite its successes, quantum physics remains, in many ways, a deeply mysterious and counterintuitive field. Its implications for our understanding of reality are profound. Quantum mechanics challenges the notion of determinism, the idea that the future is determined by the present, and introduces a universe that is, at its core, probabilistic and uncertain. It raises questions about the nature of reality itself. What does it mean for something to be in multiple states at once? What role does observation play in shaping the universe? And can quantum phenomena like entanglement tell us something deeper about the fabric of space and time? In recent years, quantum physics has become the foundation for new fields of research and technology. Quantum computing, for instance, seeks to harness the strange properties of quantum particles, such as superposition and entanglement, to create computers that can process information in entirely new ways. While classical computers use bits that represent either 0 or 1, quantum computers use qubits, which can represent both 1 and 0 simultaneously, thanks to superposition. This opens up the possibility of solving certain types of problems much more efficiently than classical computers ever could. Quantum physics has also led to advancements in cryptography, the science of secure communication. Quantum cryptography takes advantage of the fact that measuring a quantum system inevitably changes it, making it possible to create encryption systems that are theoretically unbreakable. If an eavesdropper tries to intercept a quantum communication, their very act of observation would disturb the system and reveal their presence. Quantum physics is not just a field of study.